Okay, so today we're going to sort of summarize what it is we need to know about sound waves, the key pieces of information. So I appreciate there was some of it from when we were dealing with the oscilloscopes to pick up, tie off, and then say, hey, that's what we've got to deal with. So, and also you'll have a set of notes that are worth that. So sound waves are what we covered, and let's start with sort of the basics. So sound waves are longitudinal caused bypassing vibrations through particles. Okay. And they can be measured or analysed is probably the best way. So it's analysed by using a microphone. I'm going to use a different colour. So the microphone is something that turns the sound wave into an electrical signal. The oscilloscope is the thing that displays it, and so they look like that. So that's the image of an oscilloscope, and they give us a sort of a trace. It looks transverse because that enables us to see it. We wouldn't be able to see it if we tried to display it directly as longitudinal. But where is this sort of direction? This might mean forwards and backwards, as opposed to being, sort of up and down, as it were. So it's just sort of a graph. So microphones, so we connect to an oscilloscope. Okay, and what we find is that by analysing this, there is a link between the amplitude and the volume, the frequency and the pitch. Yeah, I don't need this image. So we get the amplitude of a sound wave is linked to its volume. And the frequency of sound wave is linked to its pitch. So, and basically as amplitude goes up, volume goes up. As frequency goes up, pitch goes up. So, if someone is talking quietly, then the amplitude of the wave is a lot lower. Of course, if they're talking more loudly, then the wave would be a lot higher. And if you want to see that in action, you can feel free to go to the online oscilloscope and you can sort of like put it in. Similarly with frequency, a low frequency, very low pitch, and then you get a high frequency, and that's very, very squeaky and somewhat annoying. And so that's the sort of how shapes are doing. So, and this would be we'd be able to see if we were looking at this on an oscilloscope. You would get to the following sort of trends. So if you had something like that, so if this is our sort of normal, that's our sort of a normal sound, although your mileage for normal might vary. What we would have here is, if that would be so this here would be a louder sound of the same pitch. So we have do another one. We could do a, so we can show the same frequency, but keep the volume kind of the same. So we're comparing to our normal one. Yeah, but I reckon that's about the same. So so higher pitch. Same volume. And we could do, oh, let's use the rainbow. We could do a, no, that's terribly terrible. I'm regretting that instantly. I need a much finer pen for that. Let's get the finest pen, the finest of the fine pens. So this would be a very quiet. So, you know, this would be a very high pitch. Low volume. So simply, it's a question really of just recognizing them by sight. You know, being able to categorize. You know, if you've got some form of reference sound, which one's louder? Well, the one that's bigger in its amplitude. Which one is higher pitch? Well, it's the one. You know, where I think we could do a sort of a, yeah, let's do a final one. We could do a. So if we thought, well, what would a low pitch but loud one look like? Well, a low pitch loud one might sort of look like that. So low pitch. Louder. So we're comparing basically in an oscilloscope because what an oscilloscope is, remember, it's in this sort of like in the x direction. This is sort of measuring a time. This is sort of like in a set amount of time, how many waves are we seeing? So here we see 1, 2, we're seeing 3, 1, 2, still 3, seeing a lot more here, quite a lot here, and here we're just seeing 1.5. So that gives us an idea of like these different things, and that's what the oscilloscope sort of shows us. Sort of as things get louder, the amplitude goes up. As things get higher pitch, the waves will appear to us to be closer together because their time period will go down. So, go. Don't need you yet. Oh, so, so we can use oscilloscopes. So we can measure the time period of a sound wave. By using the oscilloscope and oscilloscope. Then calculate frequency in hertz using over time period. And that's an equation that you get given, and it's what we were doing in the last lesson. So that's sort of summing up what it is that we are doing. Now, I should make a massive, I don't know why you'll go. You can go over there. Right. Now this frequency gives us sort of the next sort of thing, because what we actually have is this idea of the range of hearing that we have. So you might notice that you have a range at which you can't hear things. And if you've got a dog whistle, or you've ever sort of like learned about like how dolphins things communicate, or you've heard of things called ultrasounds, well, the sound waves are things that we can hear, and they run in a region from 20 hertz, which is 20 sound waves per second, so still quite a lot, but all the way up to 20,000 hertz. And this is defined by the sensitivity, really, of your eardrum, your ear being able to differentiate and make sense of vibrations that fall within that region. 20,000 hertz is a very high-pitched sort of whine, and you don't really hear it very clearly. As you get older, your ability to hear this higher end sort of starts to decrease because of just old age and sort of damage to these things. So you may have heard that there are sort of examples of sort of like places where they sort of put a little speaker system, and it emits sort of really, really, really high frequency sort of sound waves, so at around about say 20,000 hertz. And the reason for doing that is if you've got somewhere that you don't want young people to congregate, then what will happen is that older people like me, who've got duffer hearing and can't hear at 20,000, I am completely happy. Whereas smaller people who have better hearing are miserable because they're hearing this sound. It's not a very nice sound. Many of the frequencies that start to get up to here, they're painful to listen to. They're not like, it's not like you can't make out someone speaking in them. They just sort of like give you just uncomfortable. And so this is something that people have done. I don't tend to agree with it as it's not particularly a great thing to do, but there is this thing: young people tend to have much better hearing at this, and then you spend years like with your headphones plugged in and just destroying your own ears. So don't do that. Now, if you listen to the human range of hearing, you will actually find that there are certain sounds that you're more sensitive to. So there'll be some sounds that you'll just you hear and you almost think they're a lot louder, but they aren't because you're just more sensitive to them. That actually also is true of color. You're more sensitive, for example, to green lights than you are to certain reds and blues. So, even with the same brightness, a green light will actually appear brighter to you because of your just eyes are slightly more sensitive to green. So, all you really need to know, and it's sort of absolutely silly, is this is actually all you need to know from it. You just need to know the range of human hearing from 20 to 20,000 hertz. You don't even really need to know this kind of definition of thing called an ultrasound. This is stuff that they use when they're scanning. So they do medical scans using ultrasounds. They're in the region of around 50,000 hertz. So there's a crystal inside an ultrasound thing that vibrates 50,000 times a second, which is just bonkers when you start thinking about it. And then there's a world of infrasounds that elephants and moles listen to. They can hear down to around about sort of 7 or 5 or 7 or something hertz. Obviously, no one can hear below 0 because there is no wave here. That makes no sense at all. And bats and dolphins, because they communicate in ultrasounds, they can sort of make sense of things at a much, much, much higher frequencies. So this is the world as we listen to it. Cats and dogs obviously a bit higher. This is essentially how dog whistles can work, because you can blow a whistle that the dog can hear, but humans can't. And there is so that's a sort of a thing that sort of is there. So, but these frequencies, high frequencies, exist, and we can measure them we can generate them and measure them on a oscilloscope. We just can't hear them anymore. So, we don't need to know about that weird sort of torture device for small people, but we will just the audible range of human hearing runs from 20 hertz to 20,000 hertz, which is otherwise known as 20 kilohertz. Sounds. No, go away, ruler. That's upsetting. Sounds of a higher frequency are called ultrasounds. And that's kind of where the term comes from. So ultra, higher sound, and the same thing is that's where we kind of get the level of things like ultraviolet and so on and so forth. Right now, so that's literally all we need to know about that. That's totally fine. I'm happy. So the next thing we need to think about is about the speed of sound. So sound travels at around about, just so you're aware, it travels at around about 330 meters per second in air. Now you never need to remember, that's not a number you need to remember, but how do you go about measuring it? 330 meters per second is quite fast. Okay, so there are kind of two methods in which that you can try and estimate and measure it. Okay, and the first is sort of the hand method. So you can measure the speed of sound by taking a large distance and being able to visibly see something and to record the time difference between when you see something happen and when you hear it happen. If you're a long distance away from something, then it takes the sound a certain amount of time to get there. So it would take this about 2/3 of a second for, if someone sort of smashed two things together, it would take 2/3 of a second for this to travel that distance. And that is actually not too bad. That's not too terrible a kind of like thing. That's if you're uncertain about 0.1 seconds, you're definitely able to detect that there is a delay between seeing this. And we can use this mostly because the time it takes for the light to travel this distance, because light travels at 300 million meters per second, as far as we care, is so much smaller than any uncertainty we have in just our delay. So we can measure the speed of sound by having this. Now, if you're ever asked, like, how do you do it? It's essentially the same as a question saying, how do you measure the speed of anything? But the key is that this distance has to be big enough. You need a distance that's at least 150 meters. Otherwise, you're just going to, otherwise, it's just going to be too uncertain. You're just going to be sort of starting and stopping the stopwatch very, very rapidly. So, so the speed of sound in air can be measured by observing a distant event, so sort of greater than 200 meters, let's say, that generates a loud. Thing. Okay, so so what we've got is we've got something that we can see and then we can hear. You start a stopwatch when you see it. You stop the stopwatch when you hear it. It is stopped. It's there. And this is actually, you can see this in effect at Sports Day, because if you think, yeah, you guys are assuming, when at Sports Day, I'm firing the starting pistol. So in a sort of starting pistol sort of thing, I will be firing something into the air, and what it will do is it will make a sound, which is great for the sort of the athletes who are sort of, ready. Let's go. I can't draw. These people look weird. They're ready and they're going to go. So they're really going to react to sound because they're only sort of like, sort of 15 meters away. But all the way over here, you've got the timekeepers. And what they can't do, if you think they're, okay, let's say they're 100 meters away. Well, it would take roughly a third of a second for them to hear the sound. So you've already gone. These people have left, and that would lead to people getting very fast times if you don't start your stopwatch until you hear the sound, because you might as well knock a third of a second off everything. So what happens is the starting pistol is meant to release some smoke, okay, at the same time. And so these people over here, they start their stopwatch when they see the smoke, not when they hear the sound. And that is something that allows them to, it sort of allows them to sort of start their stopwatch at pretty much the same time as these people here will be reacting to the sound. And that's sort of how that works. So, and that's something that's used in lots of places. Is this idea of if you've got timekeepers who aren't anywhere nearby, you use a light rather than a sound. In Olympic events, to get around the speed of sound, what they actually have is they have behind everyone's, they use an electronic starter, but behind everybody is a speaker. So everybody has a speaker behind them, so that they would detect the sound at exactly the same time, rather than it travelling across. Because otherwise, you might be in an advantage if you're in lane 1 and you're disadvantaged in lane 8. And so it's quite a lot they have to do to think about this in running events and sprinting events and so on. So anyway, so once we've done our distance between the start and finish, we would then use speed is equal to distance over time. And then if you were writing this up as an experiment, you would then say, right, okay, well, I will take repeats. I will calculate an average, do all the things that you would normally do. Now, this actually also works even if you're in water. So back in 1826 at Lake Geneva, this scientist, a guy called Collondon, and his associate, who I've got no idea who he is, they did an experiment to measure the speed of sound in water, and it's actually very, very similar. What would happen is that this hammer struck this bell, and at the same time as it's striking the bell, there was basically a little gunpowder flash that would go off. And this guy, who's on the other side of Lake Geneva, and Lake Geneva is a big lake, looked for the flash, so they sort of had a sort of timing device and looking for the flash, and then was listening to his horn to see if he could detect when the sound would reach him. And what they discovered there was that the speed of sound in water was much, much, much greater, not much, 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 but greater than it is in air. So, it's the same idea, something you can see, something you can hear, time the difference between the two events. And that's how you can measure the speed of sound in, that's a sort of experiment. Now, there is another way, and you'll find it in the CGP guide, and I've never ever seen them expect you to use this method, but we will talk about it briefly. And it involves using 2 oscilloscopes. Now, oscilloscopes are clever things. You can actually display 2 traces on an oscilloscope. There's one displaying them here. And so what you can do is you can have a generator, something that's generating sound waves, and you can put 2 microphones that are a certain distance apart. And you can display 2 traces on your oscilloscope. So you can display a trace from each one. Now the thing is the way this works is that what will happen is if you've got your sort of microphone 1, and there's microphone 2. I'm going to just colour these in a slightly different colour, red one. And we've got our sound waves that are sort of coming from this direction over here. And what they will do is they will generate some traces on our thing. So what we'll have on our oscilloscope screen is we'll get I'm going to just colour this one in blue, this first one. So we'll get a trace from the blue one, and on the screen, let's say it looks like. And then we get a trace from the red one. Now what I'm going to have this here is try and do this. So we're looking at this trace. Now the thing is, initially what will happen is these traces will not line up. So let's say that the red trace is sort of slightly off center, so it's sort of over like this. So these traces don't line up. And what you can do is you can mess around with the distance that's between these two. So you can move this one closer to or further away. And what you end up doing is when you move one wavelength apart, so when you've actually moved like one wavelength, so this distance is lambda, one wavelength, well then your two traces, because waves form a repeating pattern, will line up. So the peak will line up with the peak, the trough will line up with the trough, and what you'll get there is an ability to say, oh right, okay, these two are now in sync, because the whole wavelength is repeating again, because what you have is a moment where you've got, say, a compression there, you will also have a compression there if the distance there is one wavelength. If the distance is not one wavelength, they will be off. These two things won't line up. So you start with them sort of together. So what you do is you start with your second microphone here, and you move it along, you move it along, move it along, and you get it eventually when this lower thing matches this top one. That is when you know they're separated by one wavelength. So you can measure one wavelength. Hurrah! So you can measure lambda. What you can then do is use your oscilloscope setting, and so you can say, oh, because there'll be the squares and stuff, and you can go, oh, okay, so 1, 2, 4, 5, 6, 7, 8, whatever. You've got your squares, and you'll say, okay, with squares, you've got your x setting, and you say, oh, okay, so that you can work out, say that's sort of like 4 milliseconds. And then you can say, oh, okay, I can calculate using the oscilloscope, I can calculate the frequency. And with that, what you can therefore do is you can say, oh, right, okay, I can then use the equation V is equal to F lambda. So you get the lambda from measuring the distance between two microphones. You get the frequency from measuring using the actual oscilloscope itself, like it is. Now you'll find it's a bit of a nightmare, that practical, which is why if you're ever asked to describe this method, it's so much nicer. But if you're after the methodology of using the oscilloscope, you can find this on it's on page 37 of the CGP if you're after actual sort of like breakdown of the methodology. But essentially what it works off is being by making sure that you've got two microphones one wavelength apart, you can measure lambda, measure frequency, or measure time period, calculate frequency, and then from that you can use V equals F lambda. This is a much nicer way of doing it. And that is essentially all there really is to know about sound. So in sound, what we've got is these basics of being able to see things, and then being able to describe how to measure it, and identifying the range of human hearing. And that is it.